Good afternoon, everyone. My name is CWRU. I'm a professor at the Department of Civil and Environmental Engineering at Case Western Reserve University. So the topic of my presentation is bio-inspired adaptive pavement materials for climate resilient pavement. Okay, you see, pavements are very essential components of our community's infrastructure, but then environment, particularly the temperature, had a major influence on the durability of pavement. So as this one shows, so at high temperature, we can have more rotting on the pavement that affects the user experience. Like excessive rotting can cause an unsafe driving condition. On the other side, the pavement located inside the urban area contribute to the urban heat island effect that leads to the higher energy consumption. On the other opposite side, low temperature tends to cause cracking on the pavements, and that lead to potholes and low temperature cracks. So essentially, effectively managing the thermal boundary is important to improve the durability and mitigate the negative environmental impact of pavement structure. So we try to address this problem for effectively managing the pavement thermal boundary by inspiration from biology system. So we see some desert lizard, they adapt to the very extreme hot climate by dynamically modulating the color on their surface. So at a high temperature, so this is one example at high temperature, like the skin color of this lizard turn white, which become more reflective, while in the other side has a like a darker color that's a less reflective to the solar radiation. So inspired for this kind of a dynamic adaptive strategy, we explore this adaptive like infrastructure solar reflective infrastructure surface concept to develop adaptive infrastructure materials that dynamically modulates the infrastructure thermal envelope. So this is the maybe basis of this material is what's called a thermochromic material. So this one shows like at temperature increases, the surface appearance, the color change, which is associated with the change of the solar reflectance. On the other side, when the temperature decreases, the color of these materials become darker, which become more solar absorptive. So leverage this unique thermochromic, this is the spectral photometer analysis about the reflection spectrum of these thermochromic materials. So we see they have a very strong, so a horizontal axis is wavelength, vertical axis is the percentage reflectance. So essentially they become, these thermochromic materials can be very reflective at the infrared bandwidth. Besides, at a higher temperature, the reflectance become even higher. So this is what we hope to have for the solar modulation consideration. So essentially leverage this concept, and we explored what the thermochromic asphalt concept. So introduce this thermochromic materials into the conventional asphalt binder, make this, and then we prepare asphalt concrete with a different extent of thermochromic modulation, and then we subject the materials to the standard testing, and as well as thermal and optical property characterization. So essentially now we treated the pavement material not only just as a structural mechanical material, but also has a capability to modulate the solar reflectance, which then requires to characterize the material for multiple functional metrics. So this is the metrics we utilize to characterize the properties of this thermochromic asphalt technology, from the thermal properties, optical properties, mechanical properties, thermal performance, and also consider the upscalability for plant production. the results are pretty encouraging. So this is an example of asphalt concrete that incorporates this solar modulating thermochromic materials. So the baseline comparison is pure asphalt concrete, which has relatively low solar reflectance, while with addition of the thermochromic material to the asphalt binder, we see significant improvement in solar reflectance, particularly in the infrared range. The practical implication is this material does not have any, visually does not have any difference to the conventional asphalt concrete, but it has the ability to be more solar reflective. So with like when we introduce this material, we subject the material to the industry standard testing. So this is what's called a SuperPay performance test, which is the gold standard to evaluate the durability of the a new material for the practical application purpose. So this is just a schematic parameter design compliance to the SuperPay categorization standard. In the end, what we've observed is in a multifunctional property matrix, incorporation bioinspired solar modulating materials have a positive influence on a lot of different properties in the multifunctional matrix. So essentially, the outcome in the performance-wise is utilize this innovative thermochromic materials or thermochromic asphalt concrete. We will feature the road will feature lower summer temperature, higher temperature in the winter, and more higher performance and more durability, which also meets the SuperPay industry standard specification testing protocol. And also the material can be produced upscalable with plant production conditions. So this may be given Lowell's approach inspired from how the biology system manage the thermal boundary into manage the thermal boundary of the infrastructure components, in this case, pavement, and lead to longer durability and mitigates the negative environmental impacts of the pavement structure. Okay. Thank you for your attention.